Hello, I'm Agata Laperdiza, and I'm going to talk about two aspects that I think that make emotion recognition particularly challenging from a computer vision perspective. And these aspects are context and data bias. So I'm sure that I don't need to convince you that emotions are important, and there are many reasons why do we care about emotions and about having machines that can understand our emotions. So emotions actually play a very important role in our lives. They are very important for our communication. They are important to recognize needs in others or to anticipate to others' reactions. And besides that, emotions play a very important role in our cognition. So there are many studies showing that, for instance, emotion has a very important role in attention since it modulates our selectivity. Emotions also play a very important role in action, behavior, and decision making since they act as motivators. And in the learning process, they are very important as well. So some studies show that confusion combined with a positive emotion seems to generate motivation, while confusion with a negative emotion can lead to frustration. Or curiosity is also a state that encourages exploration and prepare the brain for learning and for remembering. And stress also plays a very important role. So low degree of a state of stress can facilitate learning, while a high degree of stress can impair actually learning. And besides that, when we imagine the AI of the future, like in science fiction movies, we always imagine these machines that interact with us in a very natural way. And for that, they have some type of social emotional intelligence. So it's natural for us to expect these machines to have these capacities of recognizing emotions and deal with them somehow. However, we know this is very challenging for a machine to recognize emotions. For us, it's something so natural. So when we look at this image, for instance, and we focus in this person, it's very easy for us to recognize some affective states in this person. Even though we don't know anything about her, we see that she seems relaxed. She is having a pleasant emotion. So she is in her apartment, sharing a nice moment with her dog. So we can understand this very easily. But for a machine, capturing these signals is so complicated. And from a computer vision perspective, most of the research for understanding others' emotions have been focused on face and facial expression analysis. And actually nowadays we have commercial systems like this one that can detect faces in a very robust way, can detect key points and analyze the configurations of these key points to recognize some common facial expression. And these methods nowadays work actually very well. And the reason why there has been so much interest in focusing on the face is because the face contains a lot of information. So we express a lot with our faces. And as an example, I want to make an experiment with you. I'm going to show you two videos of a newscaster that is telling, in one video, he's telling good news, and in another video, he's telling bad news. And I want you to look at these videos and to watch these videos and to guess when is the newscaster telling good news and when is the newscaster telling bad news. Okay, I'm sure that you found very easy this task of recognizing what video was about positive news and which one was about negative news. Actually, this was a study that we made in 2015 with David Mendoza and David Masip. And it was a small scale study, so we used 150 videos of news and we tried to make a system that could recognize just by analyzing the facial expression whether the news was good or bad. And at that moment, it worked pretty well. I'm sure that with the current techniques and technologies that we have, it would even work better. But the message here is that, okay, we have a lot of information about our emotional states in the face. However, face, it's sometimes, I mean, facial expression analysis for emotion recognition, it's not always perfect. So there are some problems. So here, I'm going to show you another example. Here we see this image. When we run the same type, so current algorithms of facial expression analysis in this image, we find this. So the system works very well in detecting this woman's face and the key points, and it returns this happiness emotion. And the reason it's because it detected a smile with a strong confidence, and that's pretty good. But unfortunately, the system does not work for this man. We don't have any output for this man. And the reason is that we have a very particular perspective of this man, is a profile perspective, so we are losing a lot of information. Plus, this man is wearing glasses, it is creating occlusions and highlights, and it makes it very difficult to detect the eyes. So facial expression analysis fails sometimes in non-frontal faces, and when we have partial occlusions or highlights or things that occlude relevant information. Let's see another problem that we can face when we analyze faces. Here's another example. So here, if you run the same type of algorithm, again, the detection of the points, it's really robust and good. But the emotion that the system recognizes is surprise. And the reason is because the mouth of the person is opened. And this is usually a prototypical view of surprise. But the reason why the mouth is open, it's not because this person is surprised, it's because this person is talking. So sometimes our face movements do not relate at all with our emotions, but with our actions. So this is what happens here, that the facial expression is not related to the emotions, but to the actions. And then there's another aspect that is even more challenging, which is the difficulty in giving an emotional meaning to an isolated facial expression. So let's see one example here. So this is, I'm going to show you some images that are from studies that Khalil Abizieh and his colleagues were performing when trying to understand the influence of context in emotion perception. In this case, so they were showing participants image like the one I show here, and they were asking people to say, what emotion do you see in this facial expression? It could be anger, it could be contempt, it could be disgust, fear. So I'm sure that if I ask you, we will not agree on what this facial expression is showing in terms of emotions. But what happens if we see more context? Well, suddenly we might agree that this is probably disgust. But what happens if I show you this image now? So it's exactly the same facial expression, but the context, in this case, the pose of the person changed. And the perception of the face is completely different. Here we see anger. And if we keep manipulating the same facial expression with different contexts, we can see different things. And actually the studies show that people perceive different emotions from the exact same facial expression. So I recommend this reading, it's very interesting. There are more studies like this one that basically show that the mapping of facial expressions to emotion categories can be strongly influenced by the same context. And this is what we were studying in this project that we call Emotions in Context. This is a project that we were working with Rona Costi, Jose Alvarez, and Adrià Recasens. And yeah, I'm going to give you some overview of this project. Okay, so in this project, we want to recognize automatically apparent emotional states, but instead of focusing on analyzing the faces, what we want to do is to look also at the context and hopefully to be able of recognizing fine-grained emotions like confidence in this case. So in the project, we are dealing with images like this one. When we can see people, we can see the face, but also we can see some context. And the idea is, okay, we want to go from images like this one to the emotions that we see in this person. For that, we wanted to use deep learning, which I mean, of course, the first challenge or problem that we had is that we didn't have any data for training or for testing. So we needed these images where we see the context, and we also have the labels of the emotions. We couldn't find any data set like this one, so we decided to create a data set. So what we did is we collected a lot of images of people doing different things in different situations. Some of these images were manually downloaded from search engines. Some others were come from public data sets like MS-COCO or 8020K. And we use crowdsourcing for annotating these images. So we designed two annotation interfaces, one for annotating discrete categories. This is the one for discrete categories. So you see the annotator can see the image and then all of these possible discrete categories, and the annotator needs to check which of these categories he or she sees in this image. And then we also had another interface for continuous dimensions annotation, in this case, valence, arousal, and dominance. And in this interface, we also collected some gender, age, so some demographics about the person that we see in the image. And after that, we came up with a data set that we call the emotic data set, which is a collection of 23,000 images and 34 annotated people, because we have some images with multiple people annotated. And with this data set, we can do several things. So there are some interesting statistical analysis that you can do of this data. For instance, this is the co-occurrence matrix. So you can see, for example, that you find a lot of instances that are labeled with affection and happiness at the same time. You also see anger and annoyance occur often together, but you see that happiness and anger rarely occur together. So this is probably noise in our data set. And then excitement and sadness, we don't have any image where we can see in the same person excitement and sadness at the same time. So you can do several types of statistics, but you can also try to model this task. So use the data set to learn a deep learning model and to see if you can do emotion recognition with this data set. And we're working with this baseline method, which baseline architecture. So this architecture basically takes as input the image, and it has two separate branches. One of them is the person features. So it has some convolutional layers to extract visual features from the person window. And then there's another one that processes the whole image and extract what we call context features. Then we merge these features, and we have just one fully connected before the output. And we have two outputs in this case, the discrete categories and the continuous dimensions. We tried different loss functions. One that worked well was for discrete categories was the Euclidean loss. So because we have a multi-label problem, so it's not a classification problem. And the only thing is that we needed to use weights because the data set is unbalanced. There are some categories that have more images than others, so we need to correct this with weights. For the continuous dimensions, also the Euclidean laws work pretty well. And the only thing is that here we have a margin. So as soon as the predicted output is close enough to the true output, then we don't backpropagate the error. And then we use also a combined loss to train in a multitask way, both the continuous dimensions and the discrete categories. And the only thing is that we have weights to balance each loss. And we performed a lot of experiments, different losses, also using just the branch of the person or just the branch of the context or the combination. And what we observe consistently is that using the body and the context is what works better when you compare it to using just the body or just the context, which makes sense. So the context is actually contributing. Here I can show you some. I mean, I'm gonna go fast in these qualitative results because actually you can see them in the paper. But here is one example where you see the ground truth. The ground truth is anticipation, confidence, engagement, and excitement. Here is just with the body. It detects more categories that are false positives. And we have a perfect recognition in the case of body plus image. This is an example where body plus image works very well. There are other examples where body plus image does not work as well. And then here are some examples where, where the recognitions do not work very well, not for the body or for the combination of the body and the context. So actually, this is a very challenging problem, and the results, so the accuracies are not very high. Some more qualitative results here, and let me highlight this one where I think that the information in this case comes basically from the context because you don't see the face here. You can estimate the pose, but you don't see the face. And the system here recognizes happiness. And this is another interesting qualitative example where, I mean, the recognition for this, for the man, in this case is pleasure, affection, and happiness. But for her, the recognition is not correct. So there are a lot of categories at fire. But the context is the same, right? So this somehow shows that the system is actually combining the information of the person and the context. Otherwise, if all the information comes from the context, this output would be the same in both cases. So the next step that we made in this project was about how to encode contextual features. So this is the baseline that I just talked about, but the next step was to focus on these context features. As I said, here we were initializing this branch with, I'm not sure if I mentioned this, but anyway, this branch was initialized with places data set since this branch is scene-centric. The branch of the person features was initialized with ImageNet since it's more object-centric. The idea here is, okay, what happens if we try to use some features that are more appropriate to encode emotional information that we can find in the context? And for that, we thought maybe we can use in this branch image sentiment analysis features. So just very briefly, let me point out the difference between emotion recognition and sentiment analysis. So when we talk about emotion recognition, what we are trying to estimate is the emotion of the person that we see in this image. When we talk about sentiment analysis, we talk about the emotion that an observer would feel when looking at this image. So sometimes these two are the same, but sometimes they are different. Sometimes they are very different, sometimes just a little bit different. In this case, so if we think about the emotion recognition, we can say that this person is probably scared and embarrassed. And in terms of sentiment analysis, we might feel worried when we see someone falling, but sometimes it makes us laugh as well. So this is an example where emotion recognition sentiment analysis is a little bit different. Okay, so there's a lot of work in image sentiment analysis. It's an active area of research, but we focused in this particular work in Sentibanks because it gave us a very nice way of extracting mid-level features for encoding the emotional information of the context. Very briefly, this work starts with 24 emotion categories, and it retrieves, the authors retrieve image and videos from Flickr and YouTube using these emotion categories. And then they keep the associated video and image tags. And they do mining in these image and video and image tags so that they collected, after this mining, they came up with a collection of nouns and adjectives that are meaningful or that appear frequently in those images and videos that were recovered using these emotion words. So because of the way they collected this, they collect these adjective noun pairs, like the ones I'm showing here. These adjective noun pairs are particularly meaningful from an emotional perspective. So colorful clouds, crying babies, so things that have an emotional impact. And at the end, the authors collected around 3,000 adjective noun pairs and around 500,000 images from Flickr per each one of these ANPs. And then they could train ANPs, so the detectors of these mid-level concepts. Originally, the authors trained these detectors with handcrafted features and linear SVM, but then there's a deep learning implementation, and this is what we used in our experiments. So here you see some results of the outputs of this sentibank, of these adjective noun pairs in some images of the emotic dataset. So they are in general pretty meaningful. And then what we did is, so this is the original model that we were working with. So we just changed the branch of the context for the features obtained with the scores of these ANP detectors. And what we observed is that the recognition of categories improved, emotional categories improved a little bit. This is in mean average precision. So it's still far from being perfect, but it suggests that that features that are meaningful for doing sentiment analysis can be meaningful and useful for encoding context information when you want to do emotion recognition in context. So as I said, this is the Emotions in Context project. We have a website, we have our data set publicly available and our models. And you can find also in the website of the project our publications. Okay, so there's another thing that I think it's very challenging when we try to create system for automatic emotion recognition, which is data annotations and biases. So most of the methods, for most of the systems, we use supervised learning. This means that we need data, and we need in particularly annotated data. But if we think just of the data, we know there's bias. So just the collection of images we use for training, or the collection of videos, they have biases. There are always biases because depending on how the methodology we use to collect the images or the videos, or the source where they come from. So there's always bias here. But there's another possible bias, which is the bias added during the annotation. So the bias of the annotations themselves. And I think that the particularity of tasks related with emotional intelligence or social intelligence is that these are subjective tasks. So when you ask annotators to annotate the emotion that they feel when observing an image, or the emotion that they see in another person when they see a person in a video, this is something subjective, and different people can perceive different things, and everything is correct. It's just what they perceive. So there's this bias created by the fact that the tasks are subjective, that is the annotator bias. And this bias is produced by the personality, the preferences, the sensitiveness of the person. Each person is different, each person perceives differently. There's another bias that happens, which is the cultural bias, and this bias also has been studied. And cultural means the bias that share populations that have common culture, common beliefs, and so on. So there's this bias as well that happen that affect the annotations. And there's the sequential bias. I'm going to talk more about the sequential bias now. The thing of the sequential bias is that usually when we ask annotators to annotate our data set, they just see a sequence of samples. So they see one sample, they label this sample, then they see another example, they label the other example. And the question is the order of the samples producing a bias? This is what we were studying with Judy Shen and Rosalind Picard in this project. So imagine that these are the samples that you want the annotators to annotate. So you show first image 1, then image 2, image 3, and so on. And the annotator produces these labels, one for each image. But in the case that you show the annotator the exact same images, but in a different order, the question is, would these same annotators produce the same labels, yes or no? And we did a set of experiments to study this effect, or to see if we observe any effect. And basically, we had two possible effects here to observe. One is the priming or assimilation effect, which means that the current perceived stimuli is closer to the previously perceived stimuli. And the other is the contrast effect, which means that the current perceived stimuli is different from the previously perceived stimuli. So as I said, we performed different experiments, and we performed them using images that we generated with the style gun. So we generated images like the ones that you see here with different subjects, 7 images ranging from sadness to happiness, and 7 images ranging from anger to happiness. So in that case, the image in the middle is neutral. And what we did is we designed this Amazon Mechanical Turk interface where annotators see the face, and they had to select the valence of this person from negative to positive with 7 categories, including the neutral. And we focused our study in the neutral images because the neutral images are the ones that are more ambiguous. Okay, so as I said, we performed a set of experiments. Experiment 1. The experiment 1 was, we had 2 groups of 20 annotators. One group of annotators saw the images in the same sequence, same order, and the other group of annotators see the images saw the images in a different sequence, but the same images. And what we did is to study the entropy of the answers. So what we observed is that the entropy is higher for the orange set, which is those that saw the images in a different sequence, which means that they agree less when they label these images. So what we observed is that the annotators that see the images in the same sequence have more agreement on the labels than those that saw the images in different sequences. On experiment 2, we had 2 sets of images, and we had 5 different random sequences of the same images. So images in set A were shuffled in 5 different sequences, and the same for images in set B. And then what we computed was the Pearson correlation between the labeled valence of the current neutral images and the previous image. And we observe a stronger signal in one of the sets, in set A in particular. But in average, what we observed is that we see a positive correlation between the labeled valence of the current image with the valence of the previous image. So basically what we observed is that we see more frequently the affect priming effect, so a positive correlation between previous image label and current image label. And finally, we made a third experiment. In this case, so is what we call the control condition. We show the sequences as you see here. So for the neutral images are the images that we are paying attention to. And the thing is that the annotators see a neutral image right after seeing K positive images, and then they see the neutral image and they see K negative images and the neutral image. And we have version A and B, which means switching the positive and the negative. So the first neutral image in version A is saw after seeing positive images, while the first neutral image in version B is the same as in version A, but annotators see before negative images. And here is one example. So annotators either see this, like positive and one neutral, or negative and one neutral. And we want to study whether the fact of seeing before positives or negatives is affecting the way you annotate the neutral images. So xj here represents each sample image. pxj means positive xj. So given, so it's the label that you give after to this xj image after seeing positive images before. And xj is the label that was given to this xj example after seeing negative images before. And what we observe is, okay, remember that k is the number of positives that you see before seeing a neutral, or the number of negatives that you see before seeing a neutral, right? And we have k equals 2, 3, and 4. So the larger the k is, the less consistency we observe on annotating the same image after positive or after negative. So the annotations actually changed. Just in for k equals to 4, we observed that just in 4% of the cases, the images got the same label. And what we see is that images usually get a higher label when you label them after seeing positive images. So after seeing positive images, you label them, you are more likely to label them as something positive. And after seeing negative images, you are more likely to label them as negatives. So again, we are observing the priming effect. So this is, so if you are interested in this study, you can read the paper that we presented last year in the International Conference on Affective Computing and Intelligent Interaction. So basically, we don't have a solution for that. We just highlight that we observe these biases exist. So the only recommendation that I can have for you in case that you are collecting data using sequences of examples is I recommend you to keep the sequence. So store this information, because maybe at some point having this information can be useful to unbias or neutralize this bias produced by the sequence. Okay, so just to wrap up the talk, I'm gonna go back to the name of this workshop, which is Challenges and Promises of Inferring Emotions from Video and from Images and Video. I talked about two challenges, which are context and data. Actually, I talked about regarding the context. I just talked about sync context, but there are other contexts that you can think of. Actually, some of the biases I mentioned can be seen as context. So, for instance, personality bias that occurs. I mean, when someone labels something, this person is affected by his own or her own personality, this can be seen as a context as well and not as a bias. So these two concepts are somehow related. And then besides these two, there's another challenge that is very important in my opinion, which is ethics. So when we work in affective computing, depending on the application, sometimes you deal with information that is very private and very sensitive. So of course, privacy is a very important aspect. In particular, you can think also that the more automatic recognition systems that we see in the world, it may happen that people suddenly, in some situations, do not want these systems to be used on them. So this is something that we need to think about as well. How can we keep the privacy of, how can we keep emotions private in a world that is full of emotion recognition systems? This is a challenge. And then another aspect related with ethics is fairness. So we have seen some computer vision systems working poorly in some populations, and this might happen as well with emotion recognition systems. So we need to be careful that systems are fair and work well for everybody. And then in terms of promises, I think I would highlight the applications, the multiple applications that emotion recognition systems have. We have seen applications in health, in education as well, and in user experience. So my feeling is that the more robust these systems are, the more they are going to be used in these areas. I think this is promising and this is exciting. And that's it. Thanks for listening.